Cameron.
Oh, yeah,
Cameron.
that is me. Right.
Is going to be telling us about Roulette for Racketeers. It looks pretty. I'm excited.
Okay, thanks, Jason. Right, so today I want to talk about Roulette, which is a discrete probabilistic programming language that supports expressive, exact, and efficient probabilistic inference. And this is collaborative work with a bunch of great coworkers of mine at Northeastern. Now, because this is RacketCon, I don't really assume that most people here are experts in probabilistic programming, or maybe don't even know what probabilistic programming is. So I'm going to spend probably most of the time kind of giving a bit of a crash course on probabilistic programming, and then also where Roulette sits as a unique language in that landscape. Okay, so a very, very, very simplified description of what a probabilistic programming language is. So imagine, take your favorite programming language, or here your second favorite programming language, Racket, and we're going to add just one single feature to the language, which is called flip. So flip, you give it a probability, which is a number between 0 and 1, and you're going to get back a Boolean, which is true with that probability, and then false with 1 minus that probability. And then the rest of the language should be approximately the same as what you're used to. But instead of getting a single value at the end of the execution, what you're going to get is a distribution over all possible values. So in this case, I'm essentially flipping a coin, a fair coin, twice, and then saying and xy, and the probability of getting true at the end is 1/4, and then false is 3/4. Okay? So that's a very, very simplified kind of probabilistic programming language. If you use PPLs more broadly, there's lots and lots of more features that they have usually. But for the purposes of this talk, that's all you need to know about probabilistic programming. Okay, so why should you care about probabilistic programming? There's perhaps two motivations. The first is that it's actually quite useful if you ever want to reason about uncertainty. And there's certain applications where that's really important. So for example, in the empirical sciences, when you do data analysis, reasoning about uncertainty and errors is very, very important. In some sense, that's really what distinguishes the empirical sciences from other modes of knowledge. In medicine, if you want to do medical diagnosis, you're also dealing with probabilities. If you have test failures, you want to know what's the probability that someone has a disease. And in manufacturing or engineering, so if you have certain components and they have some probability of failure over time, you may want to know what's the probability that something fails in 10 years or in 8 years or something like that. So there's lots and lots of applications, and we can actually model a lot of these situations using a program, which is great. There's a second motivation, which is perhaps more suitable for this audience, which is if you're a programming language enthusiast, which I think probably everyone in here is, it's just cool. I think probabilistic programming languages make you think in a different way, and I think that's just really interesting to think about the semantics of probabilistic programming languages. Okay, so I'm going to give you a more realistic example than just the flip 2 coins example, and this is a Roulette program, which looks just like a Racket program. It's implementing an interpreter for some imagined instruction set. So you have some machine that perhaps you're shipping off somewhere, maybe into space, and there's going to be some probability of failure because it gets hit by radiation or something like that. And you want to simulate what's the probability distribution over the evaluation of some program in this environment. So I write an interpreter for this instruction set, and here I can use the full features of Racket, essentially, except for one additional thing, which is I have a flip somewhere in the program, which is going to say, with some probability, instead of doing what I'm supposed to do, which is write to my memory, I'm going to just write a 0 in. Okay, this is a somewhat contrived example, but you can imagine that there are situations where you would want to write in a high-level language, this interpreter, and then just have one little area where you're going to introduce some probability, and otherwise it's going to be exactly the same. Okay, so for the purposes of this demo, here's an example program. It doesn't really matter what it is. It's computing triangular numbers using this instruction set that I've defined, and it's going to calculate the 4th triangular number. And what we want to do is we want to see, for different error rates, what is the distribution of answers that I'm going to get at the end, okay? So I have this little plot that is showing me the distribution of answers that I get from that program, given that I have an error rate of 0. And then if I want to change that, so I want to increase the error rate, then I can run the probabilistic program, and then I get a distribution over answers. And here you can see some of the other answers are coming up with very low probability. But of course, as I increase this number, so if I increase it to 4 or 8 or something much larger, now you can see that I'm getting a lot of noise. And by 0.2, I'm not getting at all the answer that I care about. Okay? So that's one more perhaps realistic example of why you want a high-level probabilistic programming language. Okay, so in order to get to how Roulette works, I want to bring you through a couple of different kinds of implementations of probabilistic programming languages in practice to kind of distinguish it from what we're doing here. And I'm going to present these in a very simplified manner. So the first one is sampling. So when I first heard about probabilistic programming, I thought you had a bunch of coworkers who were thinking about it, and I said, that seems very easy. Here's a program, and I know how to evaluate this probabilistically. I'm just going to generate a random number. So here I define flip as a function. It gets in a p, and I flip a random number here. If it's less than p, then I'll get the Boolean with the probability that I want. And then I'll just run this some number of times. In this case, I'll run it 1,000 times, and I'll just count up the distribution at the end. And that general algorithm, it's called sampling. There's lots and lots of more sophisticated algorithms that do sampling than that, but that's just the most simple version. And that's great. That totally works. You would get some kind of hash table at the end that's counting up all of the results. And that's good, but you'll notice that, well, it's not exactly the correct answer. And of course, that comes from the approximate nature of this particular algorithm is that, well, it's going to rely on what the randomness is. So we're always going to have some error. So if you increase the number of samples that you're taking, of course, you're going to get closer and closer to the correct answer, the correct distribution, but there's always going to be some amount of error. And in certain applications, for example, if you care about an event that happens with very low probability, that might be an issue. But there's ways to deal with that in sampling. But these are always going to be approximate with this particular kind of inference strategy. Okay, so the characteristics of sampling, it's very expressive. I can use all of Racket. I mean, I just define flip in this particular way and then have a little loop around the program. It can be efficient. This particular algorithm is not efficient, but there's more sophisticated ones that actually do this much more efficiently. But you're not going to get exact answers from this no matter what you do. Okay, so that's sampling. That's one algorithm. So let's say you want to get exact answers. You have another idea, which is very natural, which is, well, let's enumerate all the possible choices that we have. And that's another possible thing to do. Okay, so I have the same program here with the two flips, and I'm going to have a different search strategy. I'm going to try every possibility, okay? Now, if you did discrete math in college and you were calculating the probabilities of particular events, you may remember this kind of decision tree representation. So for every flip that we have in the program, I'm going to have a node, and then I'm going to have two branches, one which is true, which I've drawn in a solid line, and then one which is false, which I've drawn in a dotted line. And then we annotate all of the edges with the probability of that particular path. So we just draw out this entire tree, and then at the very end, we can see what the results are for each of the possible answers. And then we can calculate, based on all of the ways that you can get to that answer, what the distribution of the final result is going to be. So for true, we can see there's only one path that gets us to true, and it has probability 0.25, which is just the product of all the numbers along all the edges. And then for the other case, there's three possible ways to get there. Each of those has 0.25 probability, so we get 0.75 at the end. Now, if you're in Racket and you want to implement this, this is actually really nice because we have continuations. So at each of these flips, we can then do something similar to if you've ever implemented the AMB operator. We can use continuations in order to fork the universe and then keep track of this probability number, and then at the very end, accumulate all the probabilities and do it that way. And that's very nice. But what happens if you get a slightly more complicated program? So in the previous example, we had just 2 flips. Now we have many flips, ... So imagine we do 100 flips, maybe 1,000 flips, something like that. Okay, so this implementation now is a little bit problematic because while if we're going to search the entire space of possible ways to execute this program, while at each level we're going to be doubling the number of paths. And so if we have n flips, we're going to get an exponentially large number of paths. So if you had 100 flips, this is not going to terminate in any reasonable amount of time, even if you're clever about the implementation technique. So that's not so good. So we get the exact answer, but it comes at a cost in the sense that it's going to be proportional to the number of random choices that we make. Okay, so we got one thing, which is we got exactness. And it's expressive, so if we implemented this with continuations, then we would get to use all of Racket. But now we're no longer going to be efficient because we get this exponential blow. Okay, so let's try again. Let's try to get exactness and efficiency. And I want to show a technique called knowledge compilation that you can use for probabilistic inference that gets you those. And this is probably going to be less familiar with people. This comes primarily from this UPSLA 2020 paper, although there are some other prior work that contributes some similar ideas. And the key insight is that instead of just executing the program normally, what we're going to do is we're going to compile the program into a formula. So imagine that instead of full Racket here, we're just going to deal with a very, very small language that has flips and maybe some Boolean operations, conditionals, binding, very, very small subset that we can reasonably compile into a formula. So what we're going to do is that for each of the flips that we have, we're going to generate a new variable in this Boolean formula. So for the first flip, I'm going to generate a Boolean variable x sub 0. And along with each variable, I'm going to have something called a weight map, which is going to say, associated with this variable, I'm going to say it's associated with 0.5, so which corresponds to the parameter that we gave the flip. Okay, and so what we'll do is we'll compile this program, one construct after another. So we get to the second flip, and we'll compile that into a Boolean variable, similar adjustment to the weight map. And we compile all of these flips, okay? So constructing this formula with all of these flips is going to be pretty easy. We're just generating these variables. And then at the very end, we're going to just conjoin all of them together into this big Boolean formula and this weight map. Okay, so this is very, very efficient, just doing this compilation process as is. We're not doing anything sophisticated, no exponential blow-up. And what we need to do now is we need to take this Boolean formula and we need to be able to do probabilistic inference on it. So we need to be able to convert it to a representation where we can actually calculate the probabilities. And the other key insight of this paper is to use a special data structure in order to do this, known as a binary decision diagram, or a BDD. So a BDD is just another representation of a formula. So it's just going to be a different data structure. Instead of a syntactic representation of that formula, it's going to be this structure here. And this structure is actually going to let us do efficient probabilistic inference once we've constructed it. Okay? And one of the nice things about a BDD is that you get sharing automatically. So instead of this very large exponential tree that we saw before, the binary decision diagram is going to automatically condense this into a canonical representation that is going to be more efficient in certain cases. Certainly, for not every Boolean formula is going to have a nice compact representation, but for many of the problems that people care about, it is going to have a compact representation. And once you construct this BDD, then you can apply a procedure to it called weighted model counting that is going to calculate the probability of true and false efficiently once you've built this BDD. Okay, so that's nice. We've got exactness. This is going to give us an exact answer. It's efficient for a large class of programs, perhaps not all. But the big caveat is it's not very expressive. So I said earlier, imagine we had a very small subset of the language, which is only dealing with Booleans. So we know how for very simple kinds of constructs to compile this to a Boolean formula. But imagine if you have an arbitrary Racket program. You have lists, data structure, higher functions, macros, all of these things. Okay, we don't know how to compile all of that to Boolean formula. That seems very difficult. You can try to encode lots of these data structures, numbers, and things as vectors of Booleans and things like that, but that's very, very difficult in general. Okay, so this is kind of the picture. We've got expressiveness, exactness, and efficiency, and we've seen 3 different inference techniques that lie at the every pairwise intersection of these characteristics. So there's an obvious question, which is, well, can we get all of them at the same time? That would be amazing. And the answer is essentially yes, we can. We can get all of these characteristics at once. Of course, there's caveats, but I won't talk about them unless you ask me. Okay, so that's where Roulette comes in. Roulette is a probabilistic programming language based on Rosette that combines the power of symbolic evaluation and the knowledge compilation strategy that I just described. And by taking those two things together, we can get all 3 of these properties. So we already had a very nice keynote earlier today about talking about Rosette, so I'm not going to go into too much detail. But Rosette is a great host language for DSLs that need solver-aided capabilities. And one of the ideas of Rosette is that it kind of hybridizes 2 strategies in literature called symbolic execution and bounded model checking, which lets you get a very, very expressive language, but is able to deal with and discharge symbolic queries. So Rosette is very much like Racket. It's a subset of Racket, which is augmented with this defined symbolic feature, which is going to create a new symbolic variable. And you give it a predicate that says what kind of thing the symbolic variable is going to represent. And what you are asking for is, for any possible instantiation of symbolic variables, I want to say, does some assertion hold, or can I find some solution that satisfies some property, etc. Okay, so a little bit about how Rosette works. The key idea is that it uses this representation called a symbolic union. So when you execute this program, it's going to build up these symbolic unions, which represents values which are guarded by some particular formula. And those formulas are representing the conditions under which that value takes on the concrete value. Okay, if you know Rosette, this is slightly not true, but this is morally what's happening when Rosette executes. So here we have x0, which is going to represent a symbolic union, which is true or false, concrete Booleans, which are guarded by some formula. So here we're generating, like before, a symbolic variable x0. And so if x0 is true, we produce true. If it's false, we produce false. And we do that again for the second one. And then what's really nice is that Rosette then lifts a lot of primitive operations in the language to then work over these symbolic unions. So for example, what I can do here is I can construct a conditional based on these symbolic values. And it's going to be, if x0 is true, we're going to have 2, and if it's false, we're going to have 3. And so that y0 gets that symbolic union. And then we also have this other symbolic union, which is very similar, and now we can add them together. So plus in Rosette has been lifted to work over symbolic unions. So I can add these 2 things together, and now I get 5, 6, and 7 under different conditions. So depending on what I instantiate these symbolic variables with, I'm going to get different possible answers. So if they were both true, then I get 2 and 3, that's going to sum to 5. If I have both false, that's going to sum to 7. And then if it's true or false, so say the first one is false, the second one is true, I get 3 plus 3, which corresponds to 6. And then the other way, if it's true and false, I add 2 to 4, and then I also get 6 in another way. So at the very end, this symbolic union is essentially summarizing all possible executions, all paths through this program, depending on what assignments you make to those symbolic variables. Okay? So that's roughly how Rosette works.
Great.
So yeah, the main ideas there are when you get to a conditional, you're going to execute both of the branches, unlike in ordinary programming where you're only going to do one. And those will then get merged together into these symbolic union representations. And then the language will then lift a lot of the primitive operations to work over them. Okay, so now what we want to do is we want to adapt this symbolic evaluation strategy to perform probabilistic inference. And so if you're trying in your head to think about, well, we saw that knowledge compilation thing, we saw this Rosette thing, now what we're going to do is try to figure out how those fit together. So I'm going to take a program that looks very similar to the Rosette program we had before, except now instead of define symbolic, imagine in your head those defined symbolics are all turning into flips from before, okay? But the semantics that are going to be evaluation are going to be roughly the same. So when we get to a flip, we're going to generate precisely the same symbolic union that we had before, except now we're going to carry around this additional piece of information, this weight map, which is mapping that symbolic variable to its probability. So it's just like Rosette execution, except we're tracking some additional piece of information. And the second one, we're going to do exactly the same thing. Here's another symbolic union, and we update this weight map accordingly. Okay, and at the very end, we get exactly the same symbolic union at the end. But now what we can do is we can calculate the probabilities of each of these result values based on the Boolean formula that we have here. So we have x0 and x1. And what we can do is we look up in this weight map for their corresponding probabilities. That's 0.4 and 0.7. We multiply them together. This becomes now the probability that this program evaluates to 5. And we can do that similarly for the other branch. And then for the middle one, where we have a disjunction, we have two possible ways to get there. So what we're going to do is we're going to add up the two probabilities of each of the paths. But the secret is that Rosette's symbolic union gives us essentially this for free, this evaluation with these Boolean formulas. And then the only thing that we have to do to adjust this for inference is represent these formulas in a slightly different way. So what we do is we're going to represent those Boolean formulas using this BDD data structure, which then we can perform weighted model counting on in order to actually compute out these probabilities efficiently. Okay? So it's just stock Rosette, but with a slightly different representation for Boolean formulas for this particular application of inference. And that's essentially it. That's the secret. And then the final result is this distribution at the end. Okay, so the main takeaway from Roulette is that we're going to compile all the Boolean formulas in the symbolic union to binary decision diagrams. And then once we've compiled them to these BDDs, then in order to get the probabilities out, we use weighted model counting on them to efficiently calculate their probabilities using that additional auxiliary weight map that we tracked along the way. Okay, so Roulette brings together these two ideas from this previous knowledge compilation work, and then also symbolic evaluation strategy of Rosette in a kind of natural way. And it's funny, if you actually look at the two papers, if you look at the original Rosette paper, it's semantics, and you look at the knowledge compilation paper that I mentioned earlier, and you look at the semantics, they're actually almost identical, even though there were completely no communication between these folks. So this is kind of interesting. And so that's what really told me that there's a connection here. So the last thing to say, well, there's two things to say. One is that this is a paper, so if you're interested in the technical details, you can look at the paper. But for people in here who want to program and play with it, you can actually install it very, very easily. So this is a public package. You can Racco package install Roulette, and it will install all the dependencies that you need to run the inference engine. And there's, I think, sufficient documentation to actually use it. So yeah, if you have feedback, I'd be very, very curious to hear it. That's all. Thank you.
Awesome. We got time for questions.
Thank you.
So as a huge fan of BDDs, I'm always happy when I see BDDs. I don't really understand what's going on with the SMT because I got up to almost the end. I thought, oh, you're throwing out the BDDs and redoing everything with an SMT solver. And then the BDDs suddenly showed up and I don't even understand what Roulette is doing, Rosette is doing. I'm just completely lost about that. If you could explain that, that would be really helpful.
Yeah, so typically the use of Rosette is you evaluate the program. I'm going to get the symbolic union. I have a formula which can be given to Z3, for example.
So you just use Rosette to translate to symbolic,
Yeah.
but then you chop off the SMT and you send it to BDDs and
Exactly. So we're using the entire Rosette pipeline except the SMT solver. So C3 just goes away, and instead I'm taking
send
that
to
blank-
CUD or something like that.
Right. So we actually have a custom library for doing BDD in Rust that is doing this probabilistic inference efficiently. And so I'm
So-
sending it off to this library instead of Z3. So we're actually using a very small subset of what Rosette provides you. All of the things that are specific to SMT. Yeah, we're not actually.
How much is it buying you? What's it buying you?
So the BDD-based compilation strategy is what lets you do the weighted model counting efficiently. So calculating the vote. Yeah.
Yeah, what's the Rosette part buying you? What's the Rosette front end buying you?
So it allows me to execute essentially Racket programs for free, right? So otherwise I would have had to implement my own symbolic executor or something.
I see.
So I'm just being able to reuse that infrastructure is a huge time saver. And it means that the entire implementation of Roulette is probably like 500 lines, maybe less than 1,000 lines of code, definitely. It's very small. And so I was able to save all that work. Yeah.
Thank you.
Was there a question over? Yeah.
Two questions. Can any of this be used for continuous probability distributions? And it seems like Rosette with the symbolic unions would run into the same exponential blowup as enumeration. Is there compilation to avoid running every possible path? Like, how does that avoid that problem?
Yes. So to answer your first question, Roulette out of the box does not support continuous distributions, but we have some ideas about how that might happen. So I can tell you two ways that you could potentially recover continuous. One is that there's work on approximating continuous distributions using BDDs and a sort of piecewise approximation. Now, the advantage we had before was it was exact, and now we're approximating a distribution with exact inference, which is a little strange. But that is one possible way to go to get continuous. Another is to completely swap out the backend. So we have a BDD-based backend for discrete structure, discrete probability, but you could also target some other completely different representation. So I at least prototyped a version that used a different solver on the backend than BDDs, one called Psi, which was able to handle continuous distributions. So like Rosette's infrastructure, where you can kind of swap out the backend solver if you wanted Z3 or some other Boolvector or whatever you want, the idea with Roulette is we can also swap out and probabilistic inference engines in the backend as well to support different kinds of distributions. Your other question, I forgot. What was your other question?
It was, how does, it seems like Rosette in building that symbolic union still suffers from the exponential blowup of enumeration. Is it not running through every path?
Yes. So one of the key ideas with Rosette, and you can look at the original paper, is that symbolic unions support this type-directed merge operation. And that is what gets you savings in the end, because it's able to, instead of at every branch point, you increase the number of options that you have. At the branch point, you merge them together in a smart way. And not always, but in lots of cases, that's going to give you lots of savings.
All right. Thank you.
Was there another one on this side? Well, if there's not, where's the mini Cameron?
Yes. So Jason is alluding to the fact that, well, we have Rosette, which is a subset of Racket, and that subset of Racket happens to be large enough to copy and paste microcanon into it. And then you can add flips and do probabilistic logic programming just that way. Now, it's very inefficient, but you can completely do that, and we did that in the paper if you're interested in seeing. It does work. If you want to try it.
Use Jason's paper to eliminate beacon efficiency?
That's a good question. Maybe. Maybe stage it away.
Yeah, can we stage it away?
Yeah, maybe. That would be fun. Yeah.
All right. Well, I think we'll talk about that over the break. Let's thank our speaker one more time.